In this video, we want to clear up a couple of just final topics with polynomials, beginning with transformations of polynomial functions. And this should look very familiar with you from the quadratics unit. Transformations for polynomials can be stated in the same way as transformations for quadratics were, because all polynomial functions can be written in some form, or at least most of them can be written in a form where I have what looks like vertex form from our quadratics unit, which means if you see a polynomial written like this negative in the front tells me that this is a reflection across the x-axis. Then this coefficient right here, this 1/2, tells me that this is a vertical shrink. By a factor of 1/2. Now, if that had been a number that had an absolute value greater than 1, that had been a 3, then we would not have called that a shrink. What we would have called it, we would have called that a stretch. This number in the parentheses that's being raised to the power, this is x minus 3, tells me that this is a horizontal translation. I am moving left or right according to that number. And in this case, we're talking about x minus h. So in this case, I am moving to the right 3 units. So I'm going right 3. And this number on the end is going to give me my vertical translation. If that's a positive number, you're going up. If it's a negative number, you're going down. So this is a vertical translation up to. So transformations with polynomials can be described using all the same terms we used for quadratics. Reflections across the x-axis, vertical shrink and vertical stretch, and horizontal and vertical translations up, down, left, and right. All right, I also want to look at one more problem before we get out of this unit, and that is what happens when I'm looking for a polynomial where I know part of the zeros and I don't know the rest of them, and it doesn't tell me specifically which polynomial it wants. So here's my question. What is a quartic? Okay, so think about what quartic is going to tell me. With only 2 real zeros. And those 2 real zeros are x equals 5 and x equals 9. Okay? So I want a quartic polynomial with only 2 real zeros at x equals 5 and x equals 9. So quartic, that tells me that there are 4 solutions. There are 4 zeros. But it told me I only had 2 real zeros. Well, there are a couple of ways to do this. There are lots of possible answers. Notice that it says a quartic. That's because there are lots of different correct answers. Y is equal to x minus 5 times x minus 9 times, well, times what? Times any quadratic with no real zeros. Or duplicating one that is already used. I just can't add another real zero into this problem. Well, let's try it both ways and see what kind of quartic function we get in the end. So let's start off by saying, okay, I want to multiply this function times any quadratic function that doesn't have any real zeros. Well, what quadratic function can you think of that doesn't have any real zeros? There are lots of them out there, but probably the simplest by far would be x squared plus 1. That gives me zeros of I and negative I. So if I multiply x minus 5, x minus 9 times x squared plus 1, if I FOIL these first two linear factors, I get x squared minus 14x plus 45, and then I come back and do the distribution with my x squared plus 1, I end up with a polynomial of y equals x to the 4th power, so it's quartic, minus 14x cubed plus 46x squared minus 14x plus 45. And if you graph that on your calculator, you will see that it only has two x-intercepts. Those two x-intercepts are at x equals 5 and x equals 9. Well, what else could we do? Well, we can also duplicate zeros that were already used. Now, I can't have just one imaginary. I've either got to come up with a quadratic where both of the zeros are imaginary, or I have to not use imaginary. So one of my other options would be, since I already have x minus 5 and x minus 9 as factors, I could just repeat them. What's that going to do on your graph? It's going to mean that at both of those zeros of the function, my graph is going to bounce off the x-axis instead of going through. Well, for the first two, x minus 5 times x minus 9, I get x squared minus 14x plus 45. I get exactly the same thing when I FOIL the second two, x squared minus 14x plus 45, and then I come back and do all the multiplication for those, multiply them together, and I get this huge polynomial, x to the 4th minus 28x cubed plus 286x squared minus 1260x plus 2025. Which one of them looks like it was the easier way to do this problem? Yeah, doing these imaginary factors sure makes your problem a little smaller, a little easier to do. But you could also duplicate zeros that were already there. So lots of correct answers to that problem. Don't let that confuse you that there are many, many correct answers. So we could find a quartic knowing two of the zeros and knowing that there aren't any other zeros in my polynomial.